Derivatives of vector-valued functions. Consider a vector-valued function r of t. Then the derivative of r, where r is a vector of t with respect to t, is the limit as h goes to 0 of r of t plus h minus r of t over h. It is very easy to show, so we're not going to go through the details on this one, that if r of t equals f of t, g of t, comma h of t, then r prime of t is simply the vector f prime of t, g prime of t, h prime of t. That is, if we have a vector-valued function, to find the derivative, we can just take the derivative of each component separately. An example, let r of t equal 1 plus t squared I plus t e to the negative tj plus sine of 2tk. Then r prime of t is the following. It's the derivative of the first piece, 2t, and then I, plus the derivative of the second piece, which will correspond to j. And here we're going to need a product rule, so we have e to the negative t plus t e to the negative t times the chain out, so it's going to be minus t e to the negative t. And then plus the derivative of the part that corresponds with the k or the z part, which is 2 cosine 2t. Okay. So simply take the derivative of each component separately. Let's look at a definition, something called the unit tangent vector big T of t. Let's just look at it in 2 dimensions, but it easily extends out to however many dimensions. I have a graph of r of t. The tangent to the graph at any point is going to be r prime of t. The unit tangent vector is simply the tangent vector in that direction of r prime whose length is 1. And of course we know how to find unit vectors. In this case we're going to do r prime of t over the magnitude of r prime of t. And that's how we find the unit tangent vector big T of t. So modifying our earlier problem, where r of t equals 1 plus t squared I, and I'm just going to make it plus sine of 2tj. So it's a slightly modified version of the earlier problem. And we want to find the unit tangent vector t of t. Before we do that, we need to find r prime of t. So r prime of t is 2ti plus 2 cosine 2t j. The magnitude of r prime of t is the square root of 2t squared, 2t all squared, so 4t squared in total, plus 2 cosine 2t all squared, so 4 cosine squared of 2t. And then the unit tangent vector is simply r prime over the magnitude of r prime. So for example, we could find the unit tangent vector at a specific time, or t, doesn't have to be time, but let's say t of 0. And we can plug in, we would get 0i, I'll put the 0 there so we can see it, plus 2 cosine of 0, j. Well, the cosine of 0 is 1, so we have 2j. All over 4 times 0 squared, that's 0, plus 4 times the cosine of 0 squared, which is 4, and don't forget the square root. And this would simplify down to, and I'll leave the 0i there as well, 0i plus j. I'm going to briefly go through some properties of derivatives. I'm not going to talk through them other than to write down some of the more common ones you might see. But in general, the usual derivative rules apply. So suppose that we want to find the derivative of the product of a scalar valued function with a vector valued function. Well, it's just the product rule that you're used to. So we do f prime of t times u of t plus f of t times u prime of t. Very similar if we're taking the dot product of two vectors and we want to find the derivative. It's again just the product rule as you would expect it, u prime dot v plus u dot v prime. So we'll go back and add all the details. What if we're doing the cross product? Similar product rule, u prime of t cross v of t. Here the order matters. Make sure you get the order right when doing the cross product, plus, and then u of t cross v prime of t. So just your typical product rules. I wanted you to see those. How about the chain rule? It's similar. The derivative of u, where u is a vector valued function of f, a scalar valued function, would be the derivative of u, leaving the f part alone, times the derivative of that inside part times f prime of t. And of course, other properties will work with an exception. When you're doing, say, a quotient rule, you can't divide by a vector. So you could do a vector divided by a scalar valued function. But in general, the usual derivative rules apply. Let's look at an example using one of those derivative rules. So suppose that the magnitude of r is a constant. So the magnitude of r has to be a constant for all t. Then r prime is orthogonal or perpendicular to r for all t. In case you haven't seen the upside down a before, that means for all or for any. And let's do a proof. So here's our proof. Suppose that the magnitude of r is a constant. One thing has done a whole lot of proofs when you're doing the vectors and magnitudes is one of the first steps we do, especially if I have the magnitude of a vector, is square it, which means we need to square the other side. So c and c squared are both real numbers. Now, why do we think to square this, our magnitude? I mean, how does that help? Well, because the magnitude of something squared is simply the dot product of the vector with itself. My double barred arrow means this implies, or therefore, or thus, or whatever. So what if we have this? Now let's take the derivative of both sides. So I can take the derivative of r dot r. I'll just work on that side for now, which is going to be r prime dot r plus r dot r prime, or 2 times r prime dot r. But if I took the derivative of the other side, which is c squared, or simply a constant, I know that the derivative of this other side is 0. So what we have is that the dot product of r prime with the original vector-valued function r is 0, which implies that the cosine of the angle is 0, which means that the angle is 90 degrees, or pi over 2. And so we have proven that if the magnitude of r is a constant, then r prime will always be perpendicular to r. And let's take a look at one example, a specific example where this works. Let r of t equal cosine of t plus sine of t, cosine of t I plus sine of tj. And notice that the magnitude of r is going to be the square root of cosine squared plus sine squared, both of t, which of course is the square root of 1, or 1. So the magnitude of r is constant always. So I'm going to draw just a representative vector r. And then r prime of t is going to be negative sine of t I plus cosine of tj. And then if I do the dot product of r prime with r, we're going to get negative sine times cosine, so the x part with the x part, and then plus cosine times sine, the y part with the y part, which of course equals 0. And so if I were to draw the r prime, well, at the same ending point there, we would see that these two vectors are always going to be perpendicular to each other, even as r spins around this circle.